Famous British physicist Brian Cox has just broken silence. He's announced that the Big Bang wasn't the beginning, but something massive and terrifying existed before the Big Bang.
So I don't believe in a God. Right? However, I don't like the antagonism that occurs or is produced by this question. I mean, what you can say if you're a cosmologist, what you should say is, so we know that the universe was very hot and dense 13.8 billion years ago. We don't know how it got hot and dense. We don't even know, actually, if the universe had a beginning in time. Don't know.
About 13.8 billion years ago, the entire cosmos was a tiny, hot, dense ball of energy that suddenly exploded, according to the Big Bang theory, which first emerged in the 1920s. Over the decades, this theory has been refined, particularly in the 1980s, when many cosmologists proposed that the universe experienced a brief period of rapid expansion called inflation in its earliest moments. This inflation, caused by a peculiar form of high-energy matter that reversed gravity, expanded the universe exponentially, growing it by a factor of 1,000,000 billion billion in less than a billionth of a billionth of a billionth of a second. Inflation explains why the universe appears smooth and homogeneous on large scales. However, this raises questions about what, if anything, came before the Big Bang, and why the universe began as it did. Some see this as leaving room for the idea of a divine creator, a being beyond time and space. Others suggest that asking what existed before the universe might be as nonsensical as asking what's north of the North Pole. Although effects within the universe have causes, the universe as a whole may not have one or need one. However, this answer isn't very satisfying, and physicist Brian Cox suggests some possible scenarios. If the universe is eternal, it might not have had a beginning. If it's eternal, what role would a creator have? He suggests that something massive and terrifying existed before the Big Bang.
It's interesting, this idea of the Big Bang created the universe. That's what Einstein's theory says. That's textbook cosmology, if you like. But the current textbook picture is there was a phase in the universe's life before the Big Bang, if you define the Big Bang as the hot, dense phase from which the universe appeared to sort of burst forth 13.8 billion years ago. And that phase is called inflation. So what we think happened is that before that, the universe was accelerating exponentially fast. It means it was doubling and doubling and doubling in size. And the numbers are ridiculous. We think that if you started with a universe that was smaller than a single atom, then it would be bigger by a long way than the whole observable universe, 350 billion galaxies in it, in less than a million millionths of a second. So a very rapid, exponentially fast expansion. And when that stopped, all the energy that was driving that expansion got dumped into space. It heated it up. It produced the particles of matter out of which we are made and all the things that we see out there in the sky. And that's what we see as the Big Bang. So that sounds fanciful, but that's standard cosmology at the moment. The big question then is, well, what started the inflation? What stopped the inflation? How long did the inflation go on for? And the answer to that is, we're not sure. We don't know.
Imagine that the universe we observe is just a drop in the cosmic ocean. Beyond what we can see, there could be more space, stars, galaxies, and everything else, perhaps extending billions of light years further than we will ever access. As vast as the unobservable universe is, there are likely countless more universes just like it, varying in size and age, spread throughout an even larger space-time. As these universes expand rapidly, the space-time containing them expands even more quickly, driving them apart and ensuring they never meet. This concept, known as the multiverse, may sound like fantasy, but if current scientific understanding is correct, it is a valid idea and an unavoidable consequence of our fundamental flaws. One example of these multiverse theories is the inflationary multiverse, which describes what occurred before the Big Bang. The concept of the multiverse is rooted in the physics used to describe our observable universe. When we look into the sky, we see stars and galaxies forming a vast cosmic web. As we look further away in space, we also look further back in time. Distant galaxies are younger and less evolved, with stars containing fewer heavy elements. These galaxies appear smaller due to fewer mergers, and there are more spiral galaxies compared to ellipticals, which develop from mergers over time. At the edge of our observable universe, we encounter the earliest stars and a region of darkness where only the residual glow from the Big Bang is visible. However, the Big Bang, which occurred about 13.8 billion years ago, marked the beginning of our observable universe, not the inception of space and time itself. Before this, there was a period known as cosmic inflation, during which space expanded exponentially and was filled with energy inherent to space-time. Cosmic inflation is a theory that advanced beyond the Big Bang model by maintaining its successes and incorporating modern cosmology. It addressed several issues that the Big Bang theory could not, such as the uniform temperature of the universe, its spatial flatness, and the absence of high-energy relics like magnetic monopoles. Cosmic inflation also made several new predictions, most of which have been confirmed through observations. However, one consequence of inflation, the multiverse, remains uncertain. Inflation causes space to expand at an exponential rate, but whether the multiverse can be confirmed remains unknown. This process takes the state before the hot Big Bang and expands it significantly. This expansion helps explain the uniformity and vastness of the universe. When inflation concludes, matter and radiation fill the universe, which we observe as the hot Big Bang. However, things get complex when considering that for inflation to end, the quantum field responsible must transition from a high-energy unstable state to a low-energy stable state. This transition, moving into a lower-energy valley, brings inflation to an end and initiates the hot Big Bang. Moreover, the field driving inflation, like all fields governed by physical laws, must inherently be a quantum field. Like all quantum fields, it's described by a wave function that represents the probability of the wave spreading over time. If the field rolls slowly down the hill, the quantum spreading of the wave function will outpace the roll. This means that inflation can continue for a long time, potentially leading to more Big Bang events as time progresses. During inflation, space expands exponentially, creating more regions of space continuously. In some regions, inflation will end as the field rolls into a valley, but in others it'll persist, leading to an ever-increasing amount of space around regions where inflation has stopped. The rate of inflation is much faster than the maximum expansion rate of a matter and energy-filled universe, causing the inflating regions to eventually dominate all of space. According to the mechanisms that explain sufficient inflation to create our observable universe, there are many regions of space beyond our own where inflation has ended, and others where it continues. This leads to the concept known as eternal inflation. In regions where inflation ends, we observe a hot Big Bang that leads to a universe similar to our own. In areas where inflation persists, it creates more inflating space, resulting in regions with their own Big Bangs, which are causally disconnected from ours, and regions that continue to inflate. This idea of a vast universe, far larger than the part we can observe, constantly generating new regions through inflation, forms the basis of the multiverse concept. However, it's important to note that the multiverse itself is not a scientific theory with predictions for observable phenomena within our own universe. The multiverse is a theoretical prediction based on our current understanding of the laws of physics. It might be an inevitable outcome of these laws. In an inflationary universe governed by quantum physics, a multiverse could naturally arise. However, if our understanding of the pre-Big Bang state or inflation is incorrect, the existence of a multiverse might not follow. Nonetheless, if our current theories are accurate, the idea of an eternally inflating state, where countless pocket universes are continuously created and separated, directly results from these theories. The multiverse concept could extend beyond physics, potentially representing a new form of metaphysics. It offers insights into the limitations of what our universe can reveal. There is information we need, but may never obtain to make this testable science. Until then, we can predict but not verify or refute the idea that our universe is part of a larger multiverse. Although many aspects remain unknown, there are ways to approach the concept of the multiverse, starting with the universe itself. By definition, the universe encompasses everything. It includes all of physical existence. If it exists, it's part of the universe. Even with this broad definition, we can begin to explore the possibility of other universes. Our approach involves recognizing that the universe has a finite age and that light travels at a limited speed, setting a boundary on our observational capabilities. This boundary extends about 45 billion light-years away. However, this explanation provides only a limited view of the multiverse. There is more to the universe than what we can observe, suggesting that there are additional stars, galaxies, and possibly even intelligent beings beyond our reach. These entities exist in the universe, but are separate from our own world. In the concept of the multiverse, our universe is just one among an infinite series of universes. Imagine a giant foam, similar to the bubbles in a bubble bath. The multiverse represents this foam, continuously expanding and forming new bubbles, each representing a separate cosmos. These bubble universes all exist within the same space-time framework. Point in any direction, and past an immense distance, there's another universe, and beyond that, yet another. If this process of expansion never ceases, then the multiverse would contain an infinite number of universes. Each of those universes might have ended their local inflation in a similar way, but it's also possible that as each universe separated, it developed a new set of physics, including different forces and particles. Some of these universes might closely resemble our own, while others could be failures, filled only with void. Some may be far stranger than we can imagine, and some might be exact replicas of ours. If, hypothetically, there are only a finite number of ways to arrange all the particles in a universe, then with an infinite number of universes, repeated copies are likely. This means that not only could there be another universe in some random direction, but following that line far enough might lead to a duplicate of you doing exactly the same thing as you are right now. This idea is fascinating but challenging to test. The issue with the multiverse theory is that the bubbles representing different universes are completely isolated from one another. They exist separately, so traveling to a neighboring universe is not feasible with current technology. However, there might have been cosmic events in the distant past that could offer some insight. When our universe was young and recently separated from a larger inflation-driven expansion, it's possible that another bubble universe was nucleating nearby. If that were the case, our universes might have briefly intersected before being pushed apart permanently. While the likelihood of such an occurrence is extremely low, it's not impossible, which provides a potential method for testing the multiverse theory. Unfortunately, no observations so far have shown evidence of such a collision, which doesn't disprove the multiverse, but also doesn't provide supporting evidence. The only remaining basis we have is our theoretical understanding of the early universe, which remains incomplete. We only have a vague idea of what inflation entails, and many aspects of it, such as its driving force, the energy levels involved, and why it ended in our universe, are still unknown. Additionally, it's unclear whether inflation inevitably leads to a multiverse, or if we might be misinterpreting our own calculations. Despite ongoing debates among physicists, the concept makes for an intriguing story. Aside from the multiverse theory, there are alternatives like the cyclic universe model. This model proposes that our current observable universe is part of a sequence of universes. According to this view, our universe is expanding due to the Hubble parameter, and if this parameter remains constant, expansion will continue indefinitely. However, if the Hubble parameter is cyclical, the universe will eventually begin contracting, leading to a new hot, dense state, a new Big Bang for a new universe. In this model, the universe has no definitive beginning. It is eternal. However, the cyclic universe model has its own set of challenges. One significant issue is the problem of entropy. Entropy measures disorder within a system, and according to thermodynamic laws, can only increase. In a simple cyclic universe model, the entropy of any universe should be slightly higher than that of its parent universe. This implies that if universes cycle infinitely into the past, the current universe would have infinite entropy, which is not the case. Therefore, there must have been an initial universe with low entropy, bringing us back to the starting point. A potential solution involves introducing an overall scale factor for the universe. If this scale factor increases with each universe, the entropy issue can be resolved. This scale factor is conformally invariant, meaning it does not alter the appearance of the universe. Each universe might be twice as large as the previous one, but everything within it scales proportionally. For example, if everyone's income and the cost of everything doubles, there's no real change. This conformally invariant scale factor allows for a cyclic universe without requiring a specific beginning. The idea that each universe has a cause and that it's turtles all the way down has been challenged by a recent study. The research team examined the mathematical framework of cyclic universe models in general relativity and discovered that all such models are geodesically past incomplete. This means that according to general relativity, it's impossible to trace our universe back through an infinite cycle of previous universes. While there may have been many universes before ours, there must have been a first universe. The cyclic universe model can suggest a cause for our universe, but only shifts the question of origins further back. Even if our universe wasn't the first, some universe was. The study's findings do not apply to conformal cyclic cosmology proposed by Roger Penrose, where each universe's scale is infinitely larger than the previous one. The authors intend to explore this model next, which will be discussed in a further study. Another approach in theoretical physics is M-theory, which aims to unify various string theories and supergravity into a single, coherent framework. It is considered a leading candidate for a theory of everything, which seeks to describe all fundamental forces and particles in the universe within one comprehensive theory. M-theory has been interpreted in several ways, including as membranes, magic, mystery, and matrix, reflecting its complex and somewhat ambiguous nature. Its implications extend to cosmology, the study of the universe's origin, evolution, and ultimate fate. One major contribution of M-theory is the concept of the multiverse, suggesting that our universe might just be one of many, each with its own distinct physical laws and constants. These universes could be connected through higher dimensional spaces and might interact in ways that could potentially be observed, such as through gravitational waves or cosmic phenomena. An interesting aspect of M-theory in cosmology is the concept of brain-world scenarios. In these models, our four-dimensional universe is seen as a three-brain within a higher dimensional space. This view offers potential explanations for various cosmological phenomena, such as dark matter, dark energy, the hierarchy problem, and the initial conditions of the Big Bang. However, M-theory is not yet fully understood, with many of its mathematical formulations and predictions still speculative. One major challenge is the lack of direct experimental evidence, as the energy levels where M-theory's effects would become observable are beyond the reach of current particle accelerators. In the end, we must acknowledge our ignorance about the true beginning of the universe. Even if we consider the idea of an eternal multiverse with no definitive start, we still don't understand why there's something rather than nothing. The complexity of the universe exceeds our complete comprehension. Space is filled with celestial phenomena, some of which are incredibly beautiful, while others are intimidating. Our fear often comes from our limited grasp of these cosmic events. Here are 7 unsettling cosmic entities or phenomena. Dark matter. Dark matter is a mysterious form of matter that constitutes about 30% of the observable universe's matter energy. Despite its significant presence, little is known about it. First suggested by Swiss astronomer Fritz Zwicky in the 1930s, dark matter gained broader recognition in the 1970s when Vera Rubin provided strong evidence through her studies of galaxy rotation. What makes dark matter so perplexing is that it neither emits, absorbs, nor reflects light, making it invisible to direct observation. We infer its presence only through its gravitational effects. Dark matter influences galaxy cluster formation, affects galaxy rotation speeds, and causes gravitational lensing. Several potential candidates for dark matter particles have been proposed, including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos. WIMPs are currently the leading candidates due to their weak interaction with regular matter and their potential for detection through rare collisions. The unknown nature of such a large portion of the universe's mass is both unsettling and intriguing, driving the ongoing search for dark matter. Rogue black holes. Black holes form from dying stars that undergo gravitational collapse after they've used up their nuclear fuel. They have the strongest gravitational pull of any objects in the universe. While black holes can be found in various sizes and are often located at the centers of galaxies, not all are in these locations. Nothing can escape a black hole's gravitational pull, not even light. A particularly unsettling scenario is when a black hole roams through space independently, known as a rogue black hole. These rogue black holes are not bound to any galaxy and result from incomplete mergers between colliding galaxies. One of the few rogue black holes directly detected was observed in January 2022 using the Hubble Space Telescope. This black hole, named OGLE 2011 BLG0462, is 5,000 light-years away and has a mass about 7.1 times that of the Sun, moving at a speed of around 45 kilometers per second. If a rogue black hole were to approach our solar system, its gravitational pull could disrupt all celestial objects, including the Sun and planets. However, given the vast distances between stars and the rarity of rogue black holes, such an event is extremely unlikely. Zombie stars. Supernovas are massive explosions that occur at the end of a star's life, releasing enough energy to temporarily outshine entire galaxies. They often leave behind remnants like neutron stars or black holes. Among the various types of supernovas, type 1a is particularly interesting. These events occur in binary systems where a white dwarf accumulates matter from its companion, leading to a catastrophic explosion with consistent luminosity. Scientists have identified a subtype called type 1ax supernovae, which have lower luminosity and ejection velocity than type 1a. The remnant of this subtype is a zombie star. Supernovas are rare events, making these stars hard to observe. A significant achievement was the observation of supernova SN2012Z, a type 1ax supernova, and the first identified star system observed before it went supernova. Historical records show that supernova SN1181 was observed in 1181 AD by Chinese and Japanese astronomers. Modern astronomers, including Dana Padchik, later linked SN1181 to the nebula P30 and the central star IRAS 00500 plus 6713, now confirmed as a zombie star. IRAS 00500 plus 6713 is the only known zombie star in the Milky Way. The limited knowledge about zombie stars adds to their eerie fascination, along with their unconventional characteristics and implications for stellar evolution, though the name is more evocative than descriptive. Galaxies without dark matter. Dark matter is generally considered the invisible glue that holds galaxies together, but scientists have observed galaxies with much less dark matter than expected. DF2 and DF4 are examples of galaxies with very low velocity dispersions, indicating little or no dark matter. This finding challenges conventional theories of galaxy formation and evolution, which suggest that galaxies form within vast halos of dark matter. One study proposes that these galaxies formed due to high-velocity collisions of gas-rich galaxies, similar to the collisions that created the Bullet cluster, but on a smaller scale. In this scenario, gas separates from dark matter during the collision, and subsequent star formation creates dark matter-free galaxies. The Hubble telescope has been used to measure these galaxies accurately, but the missing dark matter remains unexplained. This raises the question, if not dark matter, what holds these galaxies together? Boomerang Nebula. The eastern Antarctic plateau in Antarctica is the coldest place on Earth, but it's still 3 times warmer than the universe's Boomerang Nebula, one of the most frigid places in space. Also called the Bowtie Nebula for its shape, it's located in the constellation Centaurus and is the coldest known place in the universe, with a temperature of 1 Kelvin, or minus 272.15 degrees Celsius. The Boomerang Nebula is a protoplanetary nebula, representing a star system transitioning to the planetary nebula phase, the final stage of stellar evolution. Scientists believe the nebula's central star is a dying red giant, emitting gas that forms the nebula. This gas outflow creates an hourglass shape illuminated by starlight. In 1995, astronomers using the ESO submillimeter telescope in Chile measured its temperature as 1 degree above absolute zero, colder than the background radiation from the Big Bang. The Boomerang Nebula's extreme cold challenges scientists' understanding of energy balance in space, as it raises questions about the mechanisms and processes at play. Strange matter is another type of matter made of strange quarks, fundamental particles. Hypothesized to exist in extreme conditions and environments like the cores of neutron stars or as isolated droplets called strangelets, it ranges in size from femtometers to kilometers. Scientists propose that strange matter forms when nuclear matter is compressed beyond a critical density, dissociating protons and neutrons into quarks. The strange matter hypothesis, also known as the Bodmer-Witten assumption, suggests quark matter is the true ground state of all matter, making it more stable than ordinary nuclear matter. Researchers are seeking observable signs to determine if neutron stars contain quark matter, which would classify them as hybrid stars. While strange matter is a compelling theoretical concept, it remains unproven, with no physical evidence yet supporting its existence. Near-Earth objects. The solar system contains various celestial objects like asteroids and comets, some of which can approach Earth during its orbit. These objects, known as near-Earth objects, NEOs, are small solar system objects that can come close to Earth when their orbits intersect or come near Earth's orbit. Scientists have discovered 23 comets passing within 0.1 astronomical units, AU, or 149.6 million kilometers of Earth. Recent examples include asteroid 2020 VT4 and 2020 AP2. The potential impact of these objects on Earth is significant, as they could enter the atmosphere and cause damage, such as creating tsunami waves or craters. Scientists have sent spacecraft to NEOs to collect samples to study their composition and understand their origin better. Initiatives like Spaceguard surveys and the Planetary Defense Coordination Office have been established to detect, track, and assess NEOs. This allows for early warnings and the development of strategies for potential deflection or mitigation. That's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode.